Hey geometers, today on the agenda we're going to talk about Cevians, and that's just a fancy word for a segment that connects a vertex of a triangle to some point on the side that's across from that vertex. Fun fact, the Cevians are named after an Italian engineer who lived in the 1700s. That's nothing you need to memorize or know or anything. I just thought it might be interesting to know where that word comes from. So we're going to look at three special Cevians today. So the first one, these are sort of in no particular order. The first one is a median. And if you think about what median means, think back to when you did statistics. The median is the middle number in a set of data when it's in order. You can think about, the median on the highway is between the northbound and southbound lanes. It's in the middle. So median, you should associate that word with middle. And then if you do, it probably makes complete sense why this is called the median, because it connects a vertex to the midpoint of the opposite side. So in a picture, it would look something like this. This segment right here would be the median. So it connects this vertex to this midpoint of the opposite side. So this segment right here is a Cevian, and it is specifically the median. So you should focus more on median than you do Cevian. So Cevian is not a term that you're going to need to be able to come up with, but you should know what it means if you see it. But median is a term you're going to need to, you may need to come up with that on your own, but you definitely need to know what it means. So that's our first special Cevian. And then our second one is an altitude. Altitude, generally, if you think about the altitude of an airplane, what that's really measuring is the height of that airplane. And when we measure height, we always measure height at a right angle to the ground. So if you think about how you would measure how tall you are, you would stand up and you would put a tape measure straight from the top of your head, straight down to the floor at a right angle to the floor. If we didn't have to measure height at a right angle, we could all be as tall as we wanted to be. Right? We could put the tape measure here and one end all the way over there, and I can make myself 12 feet tall if I wanted to. So we always measure height at a right angle. That's something that's going to come up again later in the course as well. So for an altitude, we're connecting the vertex to the opposite side so that the segment is perpendicular to the opposite side. So there's a couple things that this might turn out looking like. So here's one example. This is probably the one you were picturing. So we're connecting this vertex to the opposite side, and it's perpendicular, so it's forming that right angle. So this segment right here would be the altitude. But sometimes we have triangles that look like this, where this is sort of angled out. And in altitude here, it's not really connecting directly to the opposite side. In a case like this, you'd kind of have to imagine this side being extended out, which you will often see using sort of a dotted line. That way, represent it with a dotted line. So this is still connecting a vertex, kind of to the opposite side. It's the opposite side extended out, but it's still connecting at a right angle. These are still perpendicular. So this would be the altitude. So it's worth noting that the altitude may not actually be inside the triangle. Sometimes it's outside the triangle. Okay, and then our third Cevian is the angle bisector. And again, I think this one's pretty self-descriptive. So what this one does is it bisects the angle and then connects through to the opposite side. So this right here would be my angle bisector. So it bisects this angle at this vertex, and then it connects to the opposite side of the triangle. So those are the three special Cevians that we're going to talk about and that we're going to focus on in this course. So the other thing I want to talk about is types of triangles. So we typically classify triangles in two ways. One way is we would classify them according to their sides. And when we do this, we're talking about basically how many sides of the triangle are congruent. And if none of the sides are congruent, so in other words, if all of the sides of the triangle are different lengths, that's a scalene triangle. There's really nothing special about a scalene triangle, so we don't really talk about those that much because there's not much to talk about with them. Isosceles triangles an isosceles triangle is a triangle that has at least two congruent sides. So it has at least one pair of congruent sides. And we've seen these already. We had a theorem where we said if we have two sides of a triangle that are congruent, then the angles across from them are congruent. That two sides of the triangle being congruent, that would be an isosceles triangle. And then equilateral, an equilateral triangle, if you think right here, equa is equal, and then lateral actually means sides. So this would mean all three sides are equal. So an equilateral triangle is technically isosceles, but it's one step more specific. Because an equilateral triangle does have at least one pair, or at least two sides congruent. In fact, it has three sides congruent. So you won't see an equilateral triangle labeled as isosceles. Just so you know, if all three sides are congruent, you should call it equilateral. And then we also classify them by their angles. So if we have a triangle with every angle is less than 90 degrees, that's an acute triangle. If we have a triangle with a right angle, then that's a right triangle. And if we have a triangle with an obtuse angle in it, that's an obtuse triangle. So this example back here, where did it go? Here. This would be an example of an obtuse triangle. This would be, it appears to be, I think it's probably an acute triangle. It might be a right triangle. We don't actually know. This kind of looks like it might be a right angle up here. But this is what an obtuse triangle looks like. You don't see those very often. Okay. So let's take a look at an example where you might use some of these Cevians in a proof. So here I've got my triangle HEF, and I'm given that this segment right here, EG, is a median, and I'm also given that EH and EF are congruent. And what I want to prove is that this segment bisects this angle up here. So as with all proofs, I'm going to go ahead and label my picture with all of the information that is either given or that I can conclude from a given. So EH being congruent to EF, that's pretty straightforward. I can go ahead and mark those as congruent. Because EG is a median, I know that it splits this other side in half, right? It connects to this midpoint right here. So I can conclude from this given that HG and GF are congruent. Now, notice that I'm not given that HG and GF are congruent, but I'm concluding that from the given. And then we can also use the fact, and sometimes this is hard to see because it's hard to see maybe sometimes that this is an isosceles triangle. You kind of have to ignore the fact that that segment is right there. But triangle HEF has two sides that are congruent, which means the angles across from them, this one over here at angle H and this one over here at angle F, are congruent. And if it helps you see that, you can redraw the triangle without that segment down the middle. And now you can see, okay, that and that have to be congruent. So we're going to be able to prove that these two triangles right here are congruent by side angle side. And then what we'll be able to conclude from that then is that this angle up here, we will call it angle 1 and angle 2. That angle 1 and angle 2 have to be congruent, which is going to help us right here, because if we're trying to prove that EG bisects angle HEF, what I really need to prove first is that this angle and this angle, that angle 1 and angle 2 are congruent. And then I can go ahead and say that EG bisects angle HEF. So why don't you take a minute right now and see if you can actually write up that proof, and then you come back and compare, and we'll see how it went for you. All right, so let's take a look at the proof then. So we've got our two givens here, and then this given right here is a pair of congruent sides, so I'm going to label that with an S. And then, again, I'm going to get them in the order in my proof, in the order I'm going to need them. Since I'm going to prove the triangle is congruent by side angle side, I'm going to get them in my proof in that order. So now I'm going to go with angle H is congruent to angle F, and because those are the only angles with a vertex at, right, this is the only angle that has a vertex at H, this is the only angle that has a vertex at F, I can call them angle H and angle F. Again, if you're not sure, feel free to number them and refer to them by number. And the reason for that is, if we've got two sides of a triangle that are congruent, then the angles across from them have to be congruent. So that's my pair of congruent angles. And then my other pair of congruent sides here, I get these sides congruent because I know that medians create congruent segments. So there's my other pair of congruent segments. So again, this was not a given piece of information, but it was something that I could conclude from my given. So now that I've got my side angle side, I can go ahead and say that these two triangles, triangle HEG and FEG, are congruent. And remember, you have to make sure that you get these in corresponding order. And the reason for that is side angle side congruence. And then the next one is that angle 1 here, that angle 1 is congruent to angle 2. And the reason for that is that corresponding parts of congruent triangles are congruent. And it's not unusual for people to stop right here and think that they're done, because it feels like we've proved what we want to prove. Because if these two angles are congruent, then that makes EG a bisector, so it feels like we're done. But you're not done until you've actually said this in your proof. And I haven't said this yet, so I'm not done. So I need to go one more step and actually say and prove what I was asked to prove. So I now, because EG created congruent angles, that makes EG an angle bisector. So I can go ahead and say that EG bisects angle HEF. And the reason here is because if I get congruent angles, if it creates congruent angles, then it's an angle bisector. So a couple things worth noting about this reason. The most common mistake here is to have this backwards, to say something like if it's an angle bisector, then it makes congruent angles. And that's actually backwards from what we have. What we have here is we've got congruent angles, and because from the congruent angles, we're going to conclude that it's an angle bisector. So we're starting with congruent angles, and we're concluding that it's an angle bisector. So make sure you have this in the same order that you have this. Over here, we have congruent angles first, and then we conclude an angle bisector. So over here, we have congruent angles, conclusion, that's an angle bisector. And again, notice I have an angle bisector. I didn't just say bisector, because segments can be bisected as well. So you need to make sure you're specific in calling that an angle bisector.